All right, so I will definitely I'm recording this. Tuesday will definitely probably benefit from this as well. So the last question that I asked was uh why is this bad practice? And so one of the responses I got was you should calibrate when you take the images with the same setup. This is correct. You've heard me say this multiple times. You've heard Dr. Richards say this last week with his visit. Um, And this is something that you will find all over the web if you just do a simple Google search for it. You should always take your calibration frames with the same optical setup that you use during your actual light frames. So the difference between what we're going to be doing and uh, or the difference between what we're going to be doing and the proper way of doing it is that our calibration frames came from just the camera. Uh, all of our light frames are going to have the telescope and the camera. So, it's not too good. The positive of all this though is that we did make sure that our temperatures were set to be -5 degrees. Um, and we were pretty thorough with that. And so that actually helps take away some of that poor practice that we're doing. Because at least we have some sort of environment that's the same. All right, so all right. What we're going to do then is we will go through the notebook. I'm also going to go over what each frame is and their scientific purpose of using it. All of these words that I say are going to be really useful for you, especially when you go to do the report. So, as usual, there's this first box that has all the packages that we need in it to do all of the stuff that we're going to be doing. Uh, and then the next box you'll notice is a little bit different. There's some similarities to the last lab, but it's slightly different. This time around, I went ahead and made sure that each of these were labeled uh, as explicitly as possible. So all of my variable names have a significant meaning. For instance, this is the one that's going to have my light frames. This one's going to have my bias frames. This one's going to have my darks, and this one's going to have my flats. Okay. And then all of these for loops here, uh, they do the same thing as the last one, except we're going through our light frames, bias frames, dark frames, and flat frames, and we're storing them in these variables that we have designated as lists. So now once we do all that, we get to the actual portion of the lab where we're doing something slightly different. Well, I'd say drastically different. You're going to see this picture on your notebook. I'm probably going to post it into the assignment as well on the Canvas page, because I think that if you guys rerun this box right here, this might not show up. And that's because this is linked to a path on my computer. It's stored on there now because I ran it and it saved it. But if you reran this box, it probably won't work. So be careful until I post it. I mean, really, you could go here and you could Google calibration frame flow chart. As you can see, it tells me to resume my journey because that's exactly where I got that from. So calibration plane. And then you see here, this is where I got the image, except mine's nighttime mode. So if I scroll down here, so yeah. Uh, so what this flow chart is here for is it's here to help you or guide you through what mathematical operations you're supposed to do to your pictures, as well as or to your calibration frames, as well as how to operate and manipulate those off of your light frame to create a calibrated image. So those of you guys following my visually impaired mouse, I like it large and green like that. It's easy for me to see. We have here in the bottom left corner our light frame. A light frame is the frame that we take of the object that we're looking at. So if we go and we're looking at the Whirlpool Galaxy, and we take a picture of that, that's a light frame. So then if we follow this line all the way across, we get to calibrated. But now you see that there are some arrows here. Well, this one's kind of hard to see because it's black. But if you see here, there's arrows that point down towards this blue arrow, and it indicates that the color is getting more transferred to the calibrated side. Sorry, give me a second. If you take a look up here, we have all of the common words that we're familiar with: bias, dark, flat. And then we have master bias, master dark, and master flat. And then there's these arrows that indicate some sort of a direction, okay? And the way that you're supposed to read this is it doesn't indicate multiple numbers, but you could say that maybe light, and then you could put times 10. And then up here it says bias or offset, times 10. Dark, times 10. Flat, times 10. Because we took 10 of these, 10 of these, 10 of these, and about 10 of these. And the reason why I'm saying that is because if you look underneath each one of these boxes here, there's an arrow that says combination. And what this combination means is it wants you to take the average of all of these images. And so I did that for you in the previous lab. There was a variable where you had the averaged flat CCD sat, I think is what it was, or something there too. Or averaged flat CCD, or no, IMP or something. And that variable is exactly what you're going to need to be able to create the master frames here. So combination means take the average. So what you'll do is you'll add all 10 of your bias frames together and then divide them by 10. You'll add all 10 of your dark frames together. Then we'll do a special operation and then divide everything out. And then the same thing with the flats. So first, let me ask you guys before I talk about it. What is a bias frame? Or let me rephrase that. What information do we get from a bias frame? What does it tell us about our CCD chip? And you are free to Google things while we're in class to help you out. Here. What information do we get from a bias frame? The signal due to the electronics. Yeah, that's pretty right. More specifically, the signal that we get. So just to elaborate on this a little bit more, every time that your camera goes This is the term used to describe CCD cameras' pixel-to-pixel variation in 0 point. Each pixel has a slightly different base value, and this bias is removed using a bias frame. All right, so let's dissect what this means. When we took a bias frame, what we did was we put the cap on, we turned the lights off, and that eliminated as much as we could. It eliminated the external light. Now, the other property of a bias frame is that it's taken with the shortest exposure time. Now I'll explain. Every time the camera goes to take a picture, the electronics inside the camera run a test on every pixel. And so it activates every pixel once, at least. I don't actually know what the number of times that or how the test works, but I do know that every single time it takes a picture, it runs through all the pixels at least once. And so what that means is that we're going to get some electrons from that, or some signal that would be deemed as a count. And that's not right, because hey, those electrons aren't coming from photons that are from the object that we're trying to look at. So what a bias frame does is it tries to capture those electrons. And when we take out all the external light and we reduce our exposure time to the shortest we possibly can, we collect all of the electrons from that test, as well as a little bit of thermal electrons that we'll talk about here in a minute. So does that make sense? Is that clear? Does anybody have any questions about that? Okay. So we want to add all of those bias frames together and find the average of them. So that way we can create this next box, which is called a master bias. Okay. So now, as we can see by this arrow right here, once we've created our master bias, we can go ahead and subtract that from our light frame. And if we consider what we're doing, our progress on the flow chart, once we subtract our bias frames off the light frame, we'd be here in the calibration process. So now I want to bring your attention to this arrow here. We're not going to talk about it right this second, but I want you to just think about it. I also want you to think about it and think about what a bias is, what we just talked about. And then once we talk about dark frames, we'll go back to this arrow and see what it means. So, what's a dark frame? I leave that question to you guys. What is a dark frame? And if you're going to copy and paste from Google, try to paraphrase it. Oh, no, you're good. You don't have to apologize. I'm just saying you're not going to learn anything by copying and pasting. We do this in my 600 level class for astrophysics. We Google the questions that he asks us. He tells us we can do it, but he gives us the same stipulation. Don't give me what you see on Google. Try to tell me in your own words. Okay, Abby says that it's a photon count in darkness. Okay, but what do those photons tell us? They're not actually necessarily photons either. They're photoelectrons. Okay. So it helps to get an idea of how much noise might be in your image. This is correct. Let's elaborate on both of these. So Abby mentioned a photon count in darkness. She also just said that the temperature of the camera makes a reading of photoelectrons. This is true. All right, so let's start from the basics. What's a photoelectron? A photoelectron is if you think about the atoms in the CCD chip, each one of those atoms has some electrons in them. And what you guys will learn or have already learned from modern physics is there's an effect that Albert Einstein won the Nobel Prize for called the photoelectric effect. And you'll notice that there's that word photo in front of it's a prefix. So what photo means in this is that as a prefix, it means that the word following afterwards originated from a photon. So photoelectron means that a photon hit the atom of the CCD chip and knocked that electron off. So if we're thinking about how this actually works when we're taking images, what's going on is a photon comes in from some source, it hits an atom of the CCD chip, which I believe is silicon. There are different layers and it's a whole nother field of physics, but let's just keep it at silicon. And this photon gives that electron enough energy to kick it from the atom. That electron, which is now called a photoelectron, is then read by the camera as a signal, as a count. So this is great. This is exactly how a perfect image would be taken. However, it's not the real world. The real world is that we receive photoelectrons, but we also receive these other electrons that we're going to call thermal electrons. Really hard to say that M with my nose being congested. So thermal electrons originate from heat. And so if we're thinking about that, and we're thinking about, everyday objects that we interact with, like our laptops, our phones, if we use them a lot in one sitting, they get hot. Okay, well, the same thing happens with the camera. If you take a long enough exposure time, you're going to accrue more heat inside the camera. That heat is going to be taken by those or for lack of a better word, absorbed by those electrons, allowing them to move more and have more kinetic energy, and that they can break away from the atom themselves without a photon. This is bad because the camera can't tell the difference between a photoelectron and a thermal electron. There's no ways. So what we need to do then is we need to take a dark frame. A dark frame, remember, it has the property that the cap is on, the lights are off, and we take it for the same exposure time that we would if we were taking the light frame. So if we take a 5-second exposure of the Whirlpool Galaxy, we're going to take a 5-second dark frame as well. The reason why, actually, I want to know if y'all know, why would the exposure time of the dark frame be the same as the light frame? Based off what we just talked about with thermal electrons.
So we can determine hello?
Hey, I can hear you.
Okay. Just so we can determine how many thermal electrons are coming off the chip in the same amount of time. And so that way we can accurately correct for them.
Very good. That's perfect. That is exactly what I would say. Because that's exactly what you're doing, is you're collecting all of the thermal electrons that you would capture during the process of taking that light frame. This is also why we have a temperature reading in the bottom right corner of CCD Ops to help us make sure that every time we start to take a new picture, that we're back down to -5 degrees. All right, so perfect. So then once we've collected all of our dark frames, again, there's this other arrow that's supposed to be here that we can't quite see. Combination. And what you're doing is you're going to add all of these dark frames together. But before we can create a master dark frame, we have to consider this other arrow that I told you guys about before. And you notice that there's a little subtraction sign here. It's too small to have the word subtraction in it, so they put just a minus sign. So why do you think that there's a subtraction arrow between master bias and the combination arrow of dark frames? Think about the definition of a bias frame in that it collects all of the electrons that well, in essence, it collects all of the electrons that are used in the initialization of the chip. So why would we want to subtract the bias frames off of our dark frames?
Separate which electrons are thermal electrons from electrons from the chip.
From initialization, yes. So that is absolutely correct. Dark frames are just like light frames in that, they have the same exposure time, so therefore they have to go through the same initialization process as a light frame would. And we're trying to subtract those off of that dark frame. So that way, when we go and we, average out our dark frames, we get this master dark that we subtract from the light frame. Once we do all that, we're almost done. We have a few more things left to do. So are there any questions so far about what I've talked about? Bias frames and dark frames. I'm fighting a sneeze. All right, so this final column of frames and operations is the flat fields. So again, I'm going to ask you guys, what is a flat field in the sense of what information do we get about, what information do we get from it? Maybe if I type it in, what information? That's the question I asked.
Is it the distribution of photons across the chip?
It is, but elaborate on that a little bit more.
I'm not exactly sure I could.
That's okay. So what a flat field does is, let's think about the properties of a flat field. A flat field has the same exposure time as the light frame and the dark frame, but it has a what they call a stationary source, in that you have a constant brightness or luminosity coming from the source in such a way that you have an even distribution of counts across your CCD chip. And so when we did the last lab, we actually showed an image to ourselves of a master flat field. We didn't take into account the biases, but for lack thereof, we created a master flat field, and we saw that it was pretty much a flat, even color across or shade of white across the whole image. So how do I word this question? Why do we need a flat field? I mean, we've already taken care of initialization electrons. We've already taken care of thermal electrons. What else is left? What else is there left to correct for? I guess would be the proper question.
Does the flat field like take into account, yeah, I guess kind of what Luke said, like shading kind of from the lens or like different things like that that you can't really account for with just taking like the background of the dark field?
Yeah, this is pretty much right. I like to, yesterday I gave this example, because this is something I feel like we are all fairly familiar with. In video games, there's this thing called ray tracing. And ray tracing is something that developers have been trying to get a hold of, so that they can create light rays coming through clouds or coming through trees or things like that. Those light rays that come through the clouds or come through the trees or maybe through the window of a house that you see, that's called vignetting. It's kind of hard for me to say that. I think that it's spelled like this. And flat fields, what they do is they take care of imperfections in your optical setup. So dust, moisture, vignetting, things like that. The reason why it takes care of those things is because once you have that even distribution of photons across the chip, you can divide that out from your light frame, and you won't be able to eliminate 100%, but you can drastically reduce the effects of those imperfections in your image. So now, like we talked about with the dark frame before, the bias frames come off because by definition, the bias frames are just supposed to be the electrons from the initialization of the CCD chip. So of course we need to subtract those off of our flat fields, because the flat fields are the same exposure times as our light fields or our light frames and our dark frames. So we want to get rid of all electrons that pertain to the initialization process. We only want electrons from the source. So again, notice that once we've subtracted off all the bias frames from our flat fields, we can combine them and find the average and create ourselves a master flat field. Once we create that master flat field, we can divide it from our light frame and create our total calibrated image. So, are there any questions about this flowchart process? I kind of went over it pretty thoroughly. You have this on a recording now. I'll upload it to YouTube as soon as we're done with class.
Are we subtracting the master frames or just the frames, like the initial frames?
So the only frames that have operations performed on the light frames should be master frames.
Okay, thank you.
You're welcome. So what that means is you could technically, I mean, you should read this from left to right, top to bottom. So from left to right, top to bottom. So if you read it left to right, you'll see all these, you'll have all this, and then you go down and you go to the right. So we create our master biases, and we come over here, we combine all of our darks, subtract all our master biases off, and then we create our master dark. And then again, we're moving to the right. We create our flat fields by subtracting our biases off and then creating a master flat. And then we go down again and we go from the left to the right, and we see that from our light frame, we're supposed to subtract master bias, subtract master dark, and divide master flat. So if we continue, we see that I have partially filled out these boxes for you. I've done so to help, in a sense, keep you organized. So what you do here is, this cell in particular is the cell that you will perform your combination phase. So you combine all of your light frames together and create a master light frame. It doesn't say that here, but it should be there, and it should be right here. So you'll take, once you've found the object that you're interested in taking or processing, you will, essentially download them, load them into this light frame list, and then you'll create the averaged image here. So the same thing with the master bias. You'll combine all of them, create your master bias. For these last two, in order to create these, you're going to have to create a loop that goes through all of your dark frames and subtracts the master biases off of them. And then you combine the darks with the biases subtracted off and average it out to create a master dark. You do the same thing for the flat field. So essentially, oh, come on. Okay. So if too many people are having enough trouble, I could always go through and make that one last addition, and that being the for loops for these master darks and flats. But it would be up to you from there to figure out the rest of this, which in the next cell, you'll notice that all three of these variables are the same. So with coding, you can update your variables throughout the code. And so that's what we're doing here, is this is the phase where you subtract or divide or whatever operations from your light frames. And so once you've created your master bias, here's where you will subtract that off. Then once you've created your master dark, this is where you'll subtract your master dark off of. So once you, like, for example, if you're here and you subtract the bias off, this updates master light. So this is going to look like this. Okay. And it looks weird to us to see that master light is here both on the left and right side of the equal sign. But we're just updating master light so that way when we go to the next step, all we have to do is and so then this will update so that way you can do the next operation in simple terms there. All right, I don't want to give away all the answers. All right, so then afterwards you run this cell and it should show you your perfect image. Now you'll notice that when you go through the lab report, that it asks for your master light frame. you'll have to figure that out as well. So you'll have to add that code in. Now, some of you might be going, oh crap, how do I do all this? Well, I'm here to tell you that you have everything that you need, and it's in that last notebook. You just have to make a few changes to things. And people will tell you that that is 90% of coding is somebody else has already done the work. We can just take what they did and find a way to make it faster and use it for ourselves, or whatever strategy we're trying to administer. So you are free to use whatever resources you have. Discord is on and popping. There's lots of help going on there. I'm very appreciative of the amount of support that is going on in there. So kudos to you guys on that. It is by far and I told them last night too, the best semester for Discord. There's never been this active. So thank you guys for that. Let's see. All right, so before I continue, are there any questions about the notebook? Do you guys feel confident that you will be able to tackle this in 12 days? Barely. Well, maybe I'll have another powwow. Let's see. We still have next week to go through as well, so yeah. We will see about that. Maybe I'll create a video. I don't know. I'll figure it out. I want you guys to try to figure it out as well. Yes, we have some concern about going to the roof. I want to go to the roof too. Let's see. Unfortunately, tonight we would have been taking pictures of the horizon. If you guys ever want to know, this is the website that I use to check our weather. This is created by IBM, and there's this graduate student who is a meteorologist, I believe, somewhere here in the South. And he uses Weather Underground and follows it religiously because he feels like it's the most accurate. And I trust that because graduate students do the most work, or they do the hardest work by far. And so if he thinks it's good, it's got to be good. If this was coming from some professional that's already made it, I'd be like, whatever. They don't care. They've already made it. But this guy's busting it. I think that's who I'm talking about, Ryan Hall. That's exactly who I'm talking about. He uses Weather Underground. Yes, so if you ever want to know what I'm going to say about whether we're going to go up to the roof or not, you just go to Weather Underground, you click on hourly. The things that I look at is, the first thing I look at is precipitation. If it's, going to rain or not. And then the next thing I look at is cloud cover. Well, according to Dr. Richards, it doesn't matter now. But for stargazing, I like this number to be at 50% or less, because that means that half of our sky is covered and half of our sky is not covered. So currently 74% of our sky is covered with clouds, and that would be no good for observation. So, all right. One other thing I need to go over before I let you guys go. In the assignment portion, if you click on this link, you're going to pull this up. Well, you're going to be pulling this up. And in here is a whole bunch of objects from the Messier catalog and this IC catalog. You are free to use anything in here you want that ends with .fit or .fits. These images will work with the code. I don't think TIFF will. And so I just want to make sure I show y'all. So this one here with the .tiff, this will not work. Disregard this. This is something that I tried a while ago. So you, again, you can go through here and you can find any one of these. You'll take your master, or you'll take your dark frames, biases, and flat frames from lab 1 and apply these to this image. And then you will, essentially, you'll answer some of these questions. So let's see if we click on this. Because you guys have this video, most of this will be easy for you because well, it's literally what we went over. One thing I want to emphasize here is this. I want you guys to give me a scientific or mathematical answer here. Let me go ahead, scientific, mathematical. There we go. And then throughout you're inserting your images. So yeah, I think that kind of does it. This question as well, I want a scientific mathematical reason or evaluation of what you did. I want you to on a professional level try to think about I'm sorry, on a student level think how a professional would and try to give me an answer that way. I guess that would mean that I just don't want to see things like I took 10 pictures. They were fun. I subtracted these other 10 pictures that were fun. That's lame. Try harder. Just a little bit. I've never had anybody answer like that, which is good. I just feel like I should say that. I don't know, because I'd be lazy enough to do it. Okay, so are there any questions about anything that we've talked about this evening? You guys got an extra 3 minutes out of me than last night's class. But I also feel better today than I did yesterday. All right. Then I'm going to go ahead and stop this recording.